Welcome to the Artificial Intelligence Podcast with your host, Dr. Tony Huang. Today we're with Stelios. Stelios, can you introduce yourself?
Of course, Tony. My name is Stelios Diamantidis, and I am the Chief Product Officer at Cognichip.
So, in what ways is AI transforming the hardware design workflow beyond the routine automation that you're seeing in your field?
That's a great question, and we're seeing actually a whole new world of opportunity opening up in what we call AI-enabled chip design. The world of chip design has been evolving over the last maybe 4 or 5 decades continuously, and to the point that we can actually offer some incredible devices at geometries that were unfathomable even just a few years ago. However, the process of chip design itself, in order to evolve to this point, has had to rely on a lot of what we call divide and conquer methodologies. In other words, we chopped up the process so that we can make it easier to deal with the very deep complexity of it all. So as a result, we have now reached a point where this methodology of divide and conquer is counterproductive to our own design flows. They become too segregated, and the deep experts we've developed in any given domain have become maybe a little isolated from the horizontal process of chip design. In other words, we're still relying on a waterfall methodology for chip design, whereas other areas, let's say, for example, software, have made transition into more universal, more agile methodologies over the years.
So, how has like generative or conversational AI systems how have they been impacting like the decision making process in the chip design like space?
Yeah, so with AI methodologies and AI systems, we can go after capabilities that allow us to look at the whole chip design process more holistically, beginning to end. And by beginning to end, I really mean from the very early product definition phase, where we're ideating over what a chip could enable us to do. For example, an accelerator for a specific kind of workload, and then the entire process of taking this and turning it into high-level architecture, microarchitectures, specifications for design, RTL creation, which is our register transfer level implementation, all the way to netlist physicalization, and ultimately something that can be manufactured. So at Cognichip, this is something that we start calling artificial chip intelligence. And artificial chip intelligence is clearly a wordplay over artificial general intelligence, but it's very specific. It is the process of creating AI that can think, learn, and solve design problems at designer level cognitive skills and abilities, and can do so not only within each expertise domain or each expertise silo, but really across the design process. Give us that global visibility and that convergence to the final goal. Now, this way, not only can we become faster at designing something, but we can be much more agile in terms of changing things along the way, adding features or removing features, or becoming better at dealing with different kinds of applications upstream. Ultimately, we're estimating that the impact can be quite dramatic. We feel that there's potential, even in the short term, to reduce the time that it takes to design integrated circuits to maybe a half, and the effort, meaning the cost of designing this integrated circuits, to down to a quarter of what it is today, which would be essentially redefining for the industry.
And so, what type of like technical barriers did you encounter when you were trying to embed AI directly within the engineering tools for design?
It's a very interesting and a very, I think, challenging environment. So certainly it's going to be a process. In fact, to help us level set ourselves against that process, we broke artificial chip intelligence into 10 levels. Think of them as as a benchmark or an industry benchmark for evaluating the ability of AI to solve chip design problems. And this process goes from 0 to 9. I think currently the industry is probably at level 1, so you can think of it as a very rich roadmap forward. We feel that with the advancements we have made at Cognichip, we're touching level 4 already, And it's certainly going to be some time before we start talking about problems that can be mapped to levels 8 or level 9. Level 9 being an AI that can not only create circuits, but can also partition the logical problem of what it is that this chip does, how does it interact with software, how does they form a complete system together, and so on and so forth. So as you can imagine, when you're trying to build out systems like this, you cannot build them on top of existing technologies. You cannot take a off-the-shelf LLM that has been trained with a variety of data to perform certain general tasks, including some logic, and all of a sudden have it start designing circuits. You really need a foundation model that is purpose-built for semiconductors. And purpose-built means not only the model itself, but perhaps more importantly, the data that is used to train the model really needs to come out of these design abstractions, as we call them, this multi-story building of data views that have been evolving over the last 4 to 5 decades that allow us to perform all these engineering optimizations that are needed to build a chip. So our focus is very much in creating and delivering these foundation models. We call it a physics-informed foundation model because it performs both logical kinds of assessments and operations, but also physical, as in electrical and geometrical mappings to be able to handle the entire data stack.
And then what's the what's the balance that you like pursue when you're trying to like balance the power efficiency of your chip versus the AI capabilities when you're architecting the chips for like more complex work loads?
Yeah, I think that's one of the biggest opportunities, actually. I like to draw a parallel here. We live in a world and have been living maybe for the past year where software applications can be developed very, very quickly in the AI space and also adopted and scaled very, very quickly. You know, many examples where you had applications grow to millions of users in months and even weeks in some cases, right? So very, very fast. And you can imagine that those applications have very specific workload signatures. They offer very specific kinds of processing profiles. Now think of the hardware that these applications actually run on. It takes 2 to 3 years to get a medium complexity chip from concept to something that you can sample and test in the lab. It probably takes another year to go to volume. So 4 years. It means this applications that the application that next week we're going to hear about is going to run on on hardware that was actually designed several years ago. And that hardware, in order for that hardware to be relevant today, that hardware designed 4 years ago has to be very programmable. It also has to include a lot of features that maybe are not needed today, but were introduced to essentially, balance the risk of product fit when the chip is designed. So we have seen situations where you have a chip designed for a certain application or a certain group of applications where half the energy in the chip is actually programmability and powering features that you're not using. So think about this for a second, right? You can actually rebuild this chip in a bespoke manner, and it can operate at half the power that it's operating today, which is very profound, particularly for applications where access to a power source is maybe questionable, or applications where you have this very high scalability and you're consuming thousands and thousands of watts of power. So we feel that by collapsing the time that it takes to create chips and the associated cost, we can actually tie them closer to the software. And by doing so, we will actually make the application itself incredibly more power efficient. And I'll add one more thought to this, right? When we're working with software for any application environment out there, any AI-based application, we get tremendous value. Think of an AI application that can look at medical data, results of exams or different kinds of measurements and offer diagnosis, very high value, right? Now, think of our space. Designing a chip that works very, very well with the application actually performs a full circle between the application itself and the environment in which it runs. So you can think of a world where this becomes essentially a virtuous cycle of sorts, where an application and its hardware environment get closer and closer together, and then over time optimize each other to become even more energy efficient, faster, offer even a better user experience.
And like, how do you like debug hardware related issues that arise in these AI enabled systems?
You know, there are many aspects of debugging, and that's one of the most interesting aspects, I think, having myself been through a lot of debug in my earlier years as an engineer. Debug is a very difficult thing to do in the context of this super dense and super complex chips and systems of chips. It really comes down to an art sometimes to be able to, first of all, identify problems, that having enough observability in your environment that you find a problem, and then being able to do the root cause analysis that allows you to find where the problem came from and propose a fix for the problem. Um, for many years in the semiconductor design world, verification has been 70% of resources spent in any given project. And it is exactly for this reason. The systems are so complex that it is impossible to run every single scenario and every single potential combination of state. So you have to rely on experience, and you have to rely on systems that help you find those problems. And then once you find the problems, meaning you detect them, you have an equally difficult task, which is find how they actually happen, the reasoning behind them. So we feel it's a great opportunity for AI. AI over the years and every year has become actually very good at reasoning. So in the presence of enough data and enough of observations, and also through recent advancements in abilities to give AI tools that it can run autonomously, we can actually go out and help AI form logical hypotheses and dig into root cause analysis with a lot more autonomy than any given engineer. And that will further amplify our bandwidth and will allow us to debug these hardware systems incredibly more efficiently than we currently do. That's actually a big area where some of that three-quarters cost savings that I talked about earlier actually comes from, is verification and debug.
And what factors do you look for that are like the most critical when you're designing hardware architectures for like these AI applications?
There are a lot of factors, and I talked about product fit earlier. So in modern systems, it used to be the case actually that systems were quite general purpose. So you designed the general purpose processor, and then you pushed all the complexity into the software, but you could run all kinds of different software. With AI, we're seeing a flip of this paradigm. Now you design hardware that can be extremely efficient in running AI workloads. By implication, because AI workloads themselves can be quite different. Ideally, what you'd like to have is accelerators that actually map to the workload itself. And so that includes a process of profiling the workload, maybe grouping the workload, for optimizing the workload, and co-optimizing the workload with your target architecture. So this flexibility to go between application and architecture is extremely valuable in the world of AI. Now, of course, once you have your framework of, okay, I understand now this is how my application will work, what kinds of workloads are going to come out, and how my chip architecture is going to handle said workloads, now the question becomes, how do I build it, right? I've figured out what I want to build, but how do I build it? How do I build it quickly? How do I make sure that it actually delivers to what my front end analysis indicated that this should be able to do? And that is where the architectures themselves begin to get quite interesting. And we're even seeing cases already where AI is proposing novel architectures that we had not seen before, where it's trying to really address a very specific problem in a very creative manner and in a very custom logical kind of way. So there's a lot of opportunity for chip designers, but also folks working with AI applications to start thinking about how they can accelerate their workloads with the bespoke chips.
And like, how do you ensure like scalability when working on hardware for evolving AI workloads?
Scalability for hardware is also very, very important. So first of all, it's one of the key challenges we have to solve is our own system scalability, right? So when we're working with certain designs, we ourselves want to be able to experiment and we want to be able to pathfind. At the end of the day, the fact that we got AI that's helping us come up with some great solutions doesn't take away from the fact that most of the problems in chip design are NP hard problems. In other words, they're problems for which you cannot find mathematical solutions in real time, in a reasonable time. And hence most of them turn into a deep search kind of problem, right? You basically pathfind. It's like taking a little flashlight and walking around in a dark room. Um, and you only get to take a certain number of steps before you run out of time or before you run out of resources. So it's very important to figure out exactly where to shed that light to find that solution that you're looking for. So use of compute is extremely important. And of course, it's also equally important once you've created a new architecture, a new chip, to be able to quickly validate it with the intended workload. So the systems that we're envisioning will also be able to extend their touch into the real physical world, the world where first samples actually come into the lab and they get connected to devices that allow you to perform measurements, and those measurements can be electrical and logical. But then our systems can actually look at those interactions and help people figure out, not only whether if the part they build is what they intended to build, but whether it's actually something that works well and is manufacturable at volume.
And what's your experience when you're dealing with the hardware software co-design? Like what challenges did you come up with? I'm always curious to see like what roadblocks people get hit with when they're trying to mix things together.
Yeah, I love your analogy of mixing things together because that's sort of very close to what we've been using for many years now in the chip design world. The chip design world has had some very specific needs over the years. Once you do what we call a tape out and you send the chip out to a manufacturer, there's no patching, right? There's no, I'm going to fix this later. It's either works or it doesn't work. So our processes for building these chips and getting them to manufacturing to ensure, if possible, first silicon success are extremely important. And there's a lot of money riding on that importance. So those chips, once you get into the nuts and bolts of transistors and circuits, we have a lot of tools and we have a lot of experience in terms of making sure that they work well. But what happens at the very front end of the process, which is, specifically to your question, where rubber meets the road, means software meets hardware. Well, there are no tools in that world. At the end of the day, architects work with a variety of unstructured data. Specifications for architectures, even though we all tend to imagine that there's a beautiful PDF that includes every single aspect and every little detail of a chip, that's generally the output of a process, not the input of the process. The input of the process is more unstructured. It is more abstract, right? It can range from some high level textual descriptions of things that I would like to be able to do. It includes maybe some software traces of some experiments I ran without the hardware. It can include spreadsheets of calculations based on theoretical models. It can include the Python program that I quickly wrote to give me a data stimuli or an expected output. I'm trying to paint a picture of this world of different and very unstructured collateral that essentially come together to define to us what a system interaction should look like. So as you can imagine, there's a lot of play and there's a lot of creativity when it comes to this, and there are infinite practically dimensions of different things that you want to try. So it's also a very, very rich place of opportunity for what AI can help you with. AI has become really good at dealing with unstructured data. So it can really become essentially a co-designer for software hardware interactions, and allow us to move different knobs and different pieces, not only on the hardware side, but also on the software side, arriving at certain envelopes of performance overall that we can then turn into specifications, we can then turn into buildable things, and we can go out and we can create the different chips. and also gives us the ability to then go and specify what we call derivatives, meaning that this is my first generation of a chip, but based on all the system analysis that I was able to do, I'm going to go out and I'm going to specify a derivative for a different market, which may have fewer features, for example, but it's more energy efficient because it has fewer features and really help the front end of the system definition process.
And for the listeners at home, whenever you run an AI application, at least in my opinion or in my experience, I've always found that the hardware runs really hot because it needs to uh, like think really like think a lot and use a lot of watts. So in your opinion, like what are some like good techniques that you like employ to manage these like thermal loads in the hardware when you're running these AI applications?
Yeah, the hardware basically enables the thermal management of a lot of these things. So we've had to develop in the hardware community, first of all, new techniques for being able to allow heat to escape. So a lot of these chips were actually melting the moment you turn them on because you're running them really, really hot. And if you don't plan for some exhausts, for use of, for lack of a better word, within the chip itself, and again, we're talking miniature scale here, we're talking nanometers, right? So nano exhausts, then the heat is going to get trapped and your chip is going to melt instantly, actually. So very, very impressive when that happens. So that's one aspect. And then, of course, that applies to the more modern chips where you have multiple silicon die, multiple silicon pieces in one package. Now, the package itself has this very tough challenge of being able, of needing to be able to deliver energy into the chip, but then very quickly get the heat out. We've seen the introduction of, for example, of liquid-cooled systems. They've been around for a long time, but being able to put them on a desktop, that's impressive. More heat capacity. So heat is a huge important issue. Another technique that people use very actively right now is active thermal management. So essentially that would necessitate inserting thermal sensors in the chip and also sensors that allow you to monitor voltage and current and then use those to actively, as in the operating system level, or even the device level, um, work with load rebalancing and also with throttling performance to keep heat within a certain envelope. And that is not only good for the operation of the chip over the course of the next hour, it's important for the operation of the chip over the course of the next 3 years or as long as you expect this product to be relevant. You got to be able to prevent reliability issues from building up, and then at some point you have a catastrophic failure. From an AI design point of view, this adds more design parameters, right? So now it's not only the functionality that I have to implement, it's not only the fact that I have to fit it all in a tiny little footprint at a, as I said, nanometer scale and already sub-nanometer scale, but I have to design for all these additional requirements, the requirements of active management, the requirements of thermal versus energy, energy coming in, heat coming out, more design and optimization corners that can impact. It can basically be the difference between a product, a successful product, an economical product, and a less successful product.
So how do you balance like the performance and costs for like the AI hardware projects?
Yeah, performance and cost is always dominant, right? Traditionally, we like to think of the operating envelope of a chip in three parameters. One is what we call performance. So generally, that means speed, energy or power. So how much power we're consuming, and then finally, how much area do we take up? And area is a direct proxy to volume cost. At the end of the day, when you go to manufacture your chips, you're going to put them in what people refer to as a wafer. It's the manufacturable disk, basically, and you're going to pay a fixed amount of money for that disk. So the more chips you can fit on that disk, the less your cost is going to be per chip. So it's very, very important. Now, these three, think of them as a triangle of power, performance, and area. Um, there are a lot of embedded trade-offs in that triangle. So whenever you're trying to make a design decision, you really want to find an area of your specification where you cannot optimize one metric without a direct, reasonable impact to another metric. If you can improve performance without a penalty of energy, you don't have an optimal chip. You should find what we call the Pareto front of these trade-offs to be able to get to the very forefront of optimization. And once we do that, by the way, finding that is very, very hard. You remember the analogy with the dark room with the flashlight? Now it's more of a dark stadium or a dark warehouse with a flashlight for those. So finding the Pareto front is very, very hard. Now, once you find it, and you can mean one metric versus the other, AI can help you tremendously. It's extremely difficult to be able to map out those relationships and to be able to perform those trade-offs, but it can also be very, very valuable. So if you want to run your chip faster, it means that generally you're going to have to consume more energy. And it generally means that you're going to also have a slightly larger chip because you're going to include components that can drive more juice, if you'd like, to put it colloquially, out of your transistors. Being able to be in control of those trade-offs versus a victim of those trade-offs is extremely important for power performance and area optimization.
And then for in your experience, what's like the programming language or like high level tools that you use the most in hardware design for AI?
So let's start maybe with hardware design by itself before AI. So the industry has, for a very long time, tried to come up with high-level description languages. And depending on what people did, they had a varying amount of success, right? So some of these high-level description languages were, for example, hey, what if we were to just use software? I have a Python program, I have a C program. Can I use that to create a circuit? The answer generally is yes, in most cases, but also it is highly unlikely that that is going to be an optimal implementation, meaning you're going to be leaving PPA on the table, which is bad, as we explained before. Other folks felt that instead of creating these procedural languages, we should look for high-level structural languages. So things like UML or XML. So basically markup languages that describe the way that things fit together, and then they can be translated into constructs like gates or transistors. Again, varying levels of success because essentially when you're creating a markup language, you are creating a nice hierarchy-like structure, but the complexity tends to bubble up, right? So instead of actually designing things at the circuit level, you're just pushing all that complexity into the markup, and you end up having to unfortunately do even more work sometimes. So we are now in an environment where we don't have a clear answer as to what this high level constructs. Now, more have been developed over time. One of the more exciting ones recently was Chisel, for example, which a lot of people believe in, and it has delivered some very good results, but also has limitations. Ultimately, all these kinds of high level captures generally translate into a universally accepted what we call register transfer language, RTL. And the most popular of those is Verilog or System Verilog more recently. And all the higher level languages get translated essentially into Verilog because we have a really good flow once Verilog is captured and validated for actually taking Verilog all the way through to creating a layout and creating a manufacturable product. So now with AI, we're asked the same question again: is what is the optimal way to capture and to describe the high level operation of a system? And we at Cognichip are coming up with an answer to this problem. And essentially what we're saying is RTL is great. And RTL, we have billions of lines of RTL that have been proven through to silicon production. We should continue to leverage and use RTL. And really, the right entity for serving as a high-level abstraction language is really the model. The model itself is the abstraction and the specification, and the model itself can get us into that RTL exchange. And of course, to do that, the model itself has to understand both upstream, the high-level system descriptions, and downstream, the implications of those descriptions on the physics of semiconductors. Hence, it needs to understand the full stack.
And then last question, what do you see as like the next major breakthrough or like paradigm shift for AI and chip co-design in the next year or two?
I think we are right at the cusp that we're going to be seeing solutions of, we've already seen copilots sort of come and go, copilots being sort of mostly chatbot based entities that allow us to, get more information about something, operate a tool, maybe even create a script, this really useful but sort of smaller impact kinds of instruments. I think what we're seeing now is the advent of agents, right? We're in a world of agentic frameworks. Agents can actually become really good open APIs for creating workflows, and we're already seeing workflows, coming out and helping even in chip design become more effective. I think the whole thing will get to the next level once we have reliably delivered systems that understand how to cross the logical physical boundary. So, in essence, learn how to design things with quality of result expectation and do that with user guidance. But user guidance not as a tool, but more as I think of it as sort of a co-creator or a co-designer, meaning an equal to the designer themselves, that can be used to bounce ideas off of. It can be used to outsource entire investigations of, hey, we could do it this way. What do you think? Let me go work on it for a little bit, come back, bounce off ideas, help with very hard problems like root cause analysis and things like that. And then that will give us essentially a strong stepping stone into a future where we can accelerate the end-to-end time it takes to design chips by a significant amount.
Awesome. Well, Stelios, thanks so much for being on the show. I learned so much about it. And to the viewers at home, stay curious.
Thank you, Tony. I appreciate it. Thank you very much.